We'll now cover dynamic lateral directional stability control. The information from this topic can be found in Chapter 29 of the book. The definition for dynamic stability was how the airplane responds to a disturbance over time. When we looked at static cases, we were able to kind of separate the lateral and directional responses. But for the dynamic cases, the responses are going to be coupled, and we also have to consider the effects of the airplane's inertia. Pure rolling motion is the simplest case of lateral aircraft motion. Assume the aircraft can roll freely about its X-body axis under constant speed, straight line, horizontal motion. This is well modeled in a wind tunnel. Let's look at the equation of motion for rolling. The change in roll rate P is a function of all the parameters listed, but we can assume 4 of those are approximately 0 and simplify the equation of motion for pure rolling to the one in the middle of the page. We can then also use non-dimensional derivatives and break out a roll damping coefficient CLP, but notice that this is basically a first-order differential equation. The free motion characteristics can be studied from the homogeneous solution alone with the simple linear characteristic equation. From that, we get the characteristic root, and we can derive the time constant. The time constant of pure rolling motion depends on the roll damping parameter CLP. It's important to note that the free pure rolling response is non-oscillatory decaying response. Here's the response of the change in roll rate to a step input in aileron. We see that, again, there's no oscillations, and it's a stable mode, first order mode. Pure yawing motion is the simplest case of aircraft directional motion. Assume the aircraft is free to yaw about its CG, which is constrained to constant speed straight line motion. Again, this is suitable to be modeled in a wind tunnel. Just like we did for pure rolling motion, we can look at our equation of motion for yawing and note that some of those terms are going to go to 0. But in the end, we're given the equation in the middle of the page, and it is a second order differential equation. We can also get non-dimensional coefficients and pull out the dynamic one of CNR, which is aerodynamic yaw damping, that will drive the overall yawing motion. Our characteristic equation is going to be the second order characteristic equation, where we can pull out a natural frequency and damping ratio based on the values of those coefficients. We see that the frequency depends on the directional static stability, Cn beta, but the damping ratio depends on directional static stability and the aerodynamic yaw damping. Similar to what we did for the 3 longitudinal equations of motion, we can derive a state space model for the lateral directional equations of motion using the state space construct of x dot equals ax plus bu. In this case, our state vector will be delta beta, delta p, delta r, and delta phi. For lateral directional, we do have 2 inputs, the aileron and the rudder. In longitudinal, we just had one, the elevator. Using typical matrix algebra, we can use those equations and then define the A matrix and the B matrix based on the coefficients and inertias that we have in our equations of motion. And we can even define a term H that shows up in a lot of those coefficients. We can use Kramer's rule to solve the determinant, and it ultimately is going to result in a transfer function with a fourth order denominator with b coefficients that we could derive similar to what we did in the longitudinal case. But we'll skip that for now and jump right to the idea that that fourth order polynomial can be factored into a second order polynomial and two first order polynomials. The first order polynomials can be broken into a roll mode, a spiral mode, and then the second order polynomial will be known as the Dutch roll mode. The roll mode is a first order mode that involves rapid changes in bank angle. It determines how quickly an airplane will achieve a steady state roll rate, and it's highly convergent. The spiral mode is another first order mode which has slow changes in bank angle, and it can be slowly convergent or divergent, and it's often unstable. The Dutch roll mode is our second order mode that involves rapid changes in side slip and bank angle. It's often lightly damped and at a low frequency. On the S-plane, we can see where the modes would fall. Again, the Dutch roll mode is a complex pair, so it has a real part and imaginary part. The spiral mode is going to be close to the origin, and the roll mode is going to be on the real axis in the left half plane, but away from the origin. This diagram describes the roll mode in more detail. But basically the roll rate is more dominant than the yaw rate, so the motion is almost purely roll. It's an important measure of rolling performance. It's characterized by small time constants, which means fast motion. It's an exponential response, so no oscillation, and it's always stable. Here's the roll mode again displayed on the S-plane on the top. It's on the real axis and away from the origin. If the aircraft is given a step input and aileron, you can see the roll rate response at the bottom. The roll mode time constant, tau r, is the time it takes to get to 63% of the steady state roll rate. Here's how the roll mode would look on flight test strip charts. It would be initiated with an aileron step input. We would then look at the roll rate to determine how quickly a steady state roll rate is reached, and we would see that the bank angle would continue to grow at the constant roll rate. The spiral mode involves aperiodic changes in heading and direction of travel after an initial bank angle disturbance. If the aircraft is stable, it's characterized by the time constant. If the spiral mode is unstable, it's characterized by the time to double amplitude. Either way, the response is going to be exponential with no oscillations. It's going to be relatively slow, but it can be unstable. And it's the cause of many accidents in the early days of aviation. Pilots often control this type of unstable spiral mode subconsciously. Here's a diagram that depicts how the spiral mode builds over time. Here's another diagram to provide more detail into the spiral mode. The airplane bank angle increases slowly, which causes the side slip angle to increase, and the airplane flies in a tighter and tighter spiral. We said that the spiral mode is an exponential response, which means there's no oscillations. If it's stable, and there's a bank angle disturbance, then the response will eventually go to 0 bank angle. If it's unstable, the bank angle will grow over time, and it will eventually go unstable. On the top plot on the S-plane, if the x is in the left half plane, then it will be a stable response. If the x moves to the right half plane, it will be the unstable or divergent response. Here's some typical time history data showing the spiral mode. The mode was initiated with an impulse in aileron that caused an initial roll rate and caused the bank angle to go to the position of about 7 degrees, and then the controls were released. And we see that the bank angle then, over time, drifted back toward wings level. Next, we'll talk about the Dutch roll mode. It's a second-order oscillatory motion that is coupled side-slipping, rolling, and yawing motion after an initial disturbance in beta. It may be lightly or heavily damped, and it's going to have an associated frequency and damping ratio, but it's the prominent mode in lateral directional flying qualities. Again, on the S-plane, the Dutch roll is a second-order complex pair, so it has a real part and imaginary part, and it's typically initiated in flight with a rudder doublet. The Dutch roll is often best seen by just looking out the wingtip after a rudder doublet and watching the motion of the wingtip as it scribes ellipses on the horizon. The Dutch roll was named for the characteristic side-to-side motion of ice skaters on the wintry frozen ponds of the Netherlands. Here's some time histories you would see in flight test where the Dutch roll was excited using either an aileron or rudder doublet, and you would look at yaw rate, roll angle, and side slip angle beta over time, and notice that there's relatively rapid changes in bank angle and side slip. Just like for the longitudinal case, simpler models can be developed for the lateral directional modes that give us insight into the effects of the stability derivatives on particular modes and are often useful for control design. Each mode has a dominant set of states contributing to the response. For roll mode, primarily rolling motion. Other responses is very small. For spiral mode, primarily bank turn motions, R and phi. Dutch roll mode, primarily side-slipping beta and yawing motions. The roll mode can be approximated by a 1 degree of freedom pure rolling motion. There's a lot of details here, but ultimately we can come up with an estimate for the time constant, the roll mode time constant, as negative 1 over LP. The roll damping LP or CLP determines the time constant of the roll mode. The spiral mode can be approximated by neglecting rolling motion and side slip rate. And ultimately we can derive an equation that shows our change in R dot is a function of L beta n delta R minus L delta R n beta over L beta times the change in rudder deflection. We see that the time constant for the spiral mode is then negative L beta divided by L beta nr minus LR n beta. It's a very slow mode. The spiral mode is going to be stable if that quantity is negative. Airplanes with lateral static stability have CL beta negative. So spiral mode requires CL beta times CNR to be greater than CLR times CN beta. So increasing the dihedral effect CL beta or the yaw damping CNR makes the spiral mode stable. The Dutch roll mode can be approximated by assuming the motion entirely consisting of side slip and yaw. So we can reduce our state space model to just a 2x2 A matrix and a 2x2 B matrix. Solving the determinant using Cramer's rule, we can get equations for the natural frequency of the Dutch roll and the damping ratio of the Dutch roll, and those equations are shown below in the blue boxes. We see that the dihedral effect CL beta is driving the lateral static stability. We need that to be negative. But if the magnitude of CL beta becomes too big, the Dutch roll root moves into the right half plane and the Dutch roll becomes unstable. The spiral mode becomes more stable, so there's a trade-off between lateral static stability and dynamics Dutch roll stability. Cn beta is driving the directional static stability, and we need that to be positive. But increasing Cn beta makes the spiral mode less stable and increases the frequency of the Dutch roll. So now there's a trade-off between static directional stability and dynamic spiral mode stability. Now let's look at what the FAA says in terms of dynamic stability and the Dutch roll. Basically, it needs to be damped to 1/10 amplitude in 7 cycles, and that's both controls free and controls fixed. The FARs do not address the spiral mode, but military specification states that the time it takes for the bank angle to double after a small disturbance should take at least 20 seconds. Our flight test technique involves holding lateral control fixed and achieve a 5 degrees of bank angle using rudder. The rudder is then released to trim and all other controls are released, and then we just basically time the bank angle and look at it. We'll note what the bank angle value is 20 seconds after the controls are released, and then we'll just qualitatively describe the response. For Dutch roll, we'll excite the Dutch roll using either a rudder kick or a rudder doublet. Both the number of cycles to damp to half amplitude and the roll to side slip ratio can be obtained from visually observing the aircraft wingtip during the oscillation. If the airplane has a data acquisition system, record side slip beta, bank angle phi, and the rudder deflection delta R over time. If you have a smartphone, simply film the wingtip after the rudder doublet and observe the response. The damping ratio of the Dutch roll can be found using the half cycle amplitude chart on the right. You can get the undamped natural frequency using the damped frequency that you observe and the damping ratio that you calculated and the equation shown. For the Dutch roll mode, the military specification requires 2 parameters, C sub 1/2, which is a function of the Dutch roll damping ratio, and the other parameter is phi over the equivalent airspeed, which is 57.3 over the equivalent airspeed times the phi to beta ratio. Knowing those 2 parameters, you can then plot them on the graph shown on the right and verify that the specification is met.